Anyway, so I will continue. Yes, so I'm a researcher in Skolkovo Institute of Science and Technology. And since the last time we met, like in March and now, and during this time, I have defended my PhD and I have got my degree in PhD. My topic was research on tokenized supply chain and blockchain. So today's today's blockchain seminar is the little bit of work that I have done uh, after my PhD defense. And so, yes, today I'll be presenting you my topic, which is leveraging IoT and blockchain for autonomous gasless transactions in supply chain system. So this will be talking on the area of supply chain, and let's have a look what we'll be seeing in today's lecture. My slide is changing, right? And
Yes,
it's fine.
That's fine.
Great. So this work is reference of the previous three work which we have done. Two of them have been published, and third one is under print. So let's hope that will be published soon. First two work talks about blockchain and IoT. First one being a full, first one on 2023, for being the full detailed thing. And the second paper was more of a demo version, where we have the front end dashboard, which will be also shown in later part. And third part, which is on 2024, that is empowering autonomous IoT devices in blockchain through gasless transaction, is more on a build up on the first two research in this slide. Okay, so what are we going to see today? When IoT met blockchain, we will be looking into gasless transactions. We will look into some more future directions, what we further plan to do in our research. So when first thing that we talk, when IoT met blockchain, so what was the necessity, that what was the actual requirement that we had to kind of give a introduction of, like, why you should have an IoT and blockchain together? First thing was inefficiency due to manual processing. So IoT-based systems are also centralized, and there is a problem of real-time responsiveness. Now, let me tell you one by one, what do we mean? So to have something manually processed, it takes time. So for example, if you have an IoT device and you try to make some interaction through the blockchain, there is a kind of manual interaction that will be required. For example, approving your transaction on wallet to interact with the blockchain. It's a simple example. IoT devices are definitely centralized, and because of this centralized architecture, they're vulnerable to tampering. What does it mean? So a centralized system can have a single point of failure. So if all the other IoT sensors are connected to this centralized IoT device, and if the central IoT device is compromised, let it be by anything, like maybe some attack happens, or like some hypothetical situation that this device is compromised. So other remaining sensors goes useless for this situation. There can be cyber attack, and there can be inefficiencies in sensitivity. What does it mean? These sensors can be actually manipulated somewhere by creating a fake scenario because of its centralized nature. This is our assumption. And to have a real-time responsiveness, it is also problem because of IoT devices. We should have a fast responses and some information. And so in general, IoT, first of all, is designed to have fast response, fast real-time providing scenario. Like they should provide everything on time. So to have a blockchain system, which takes a lot of time somewhere to have transactions in waiting time and so on. So that is where we find it necessary to have IoT devices integrated with blockchain. Right. So when we talk about the universal decentralized application, there are some different parts that are on board. So you have a front end, you have a wallet, you have a smart contract that is running on Ethereum virtual machine, which is kind of working on a blockchain environment. So in the traditional way, that you have an actor who is interacting with an application, and inside application you have wallet and website, right? A simple scenario, and they interact with blockchain. A wallet can be as simple as MetaMask or Wallet Connect, a simple scenario that we produce here. So the problem that we see in in IoT integration with blockchain, that even if using this architecture, and even if you include the IoT device, it has a problem of incompatibility with basic interfacing. So what does it mean? So many IoT devices, they either have no display or like they are like headless display, like yes. So they have minimal UI capabilities, right? So therefore, to interact through interface, let's assume if you're talking about a browser. So a browser requires some sophisticated interface to kind of have a rendered web content property, which IoT devices often cannot support. So because of this, it further leads to poor or unstable user experience. Right. Second scenario could be the security risks. So they have, again, if we talk about interface in terms of browser, they have broader attack surface, right? So IoT can be subjective to malware, phishing, or like browser vulnerability. It is possible. Third is interactive complexity, because somewhere when you, if you have experience in making some decentralized application, whenever you interact with the application, you should go through a wallet connect. For example, MetaMask or wallet connect, yeah, through wallet. So there it requires a manual approval. That means you move your mouse. If you talk about the computer browser, you click approve, and then your browser is interacting with the blockchain, and the further transaction things can process. Right. So IoT cannot have this thing, because that is where sometimes the security, how to say, like captcha comes into place. Like, are you not a robot? Technically, that is like stopping you. Third one is can be value error. Now, what do we mean by value error? Uh, Even if in this scenario you include a person, like in this case, for example, if you have a device, you have an actor who is reading the device, who is reading the value from the device and manually processing to the blockchain, there can be a value error. So for example, very common and most error that people can make, like for example, if a person who is doing this work gets up early in the morning, comes for morning and messes up the number, for example, T324, and by mistake he puts 342. So it's a mistake he makes, right? It was not intentional, but it can happen. We all are humans, too prone to make mistakes. Second example could be corruption to make mistakes. For example, on purpose, this person manipulates and puts some information onto the blockchain, right? So this is the scenario that we have the problems in integration with the blockchain at the situation. So to mitigate such type of problems, and not to have such scenario, we have introduced to you a DOIT, a decentralized IoT. This is how you can pronounce DOIT, with the phonetics down over there. So yes, so what exactly DOIT is going to do? It is going to eliminate the external wallets that will enable the IoT device to automatically sign the transaction. Instead of having a traditional architecture, like you have a device, or like if you had this long architecture, or like device, actor, wallets, and blockchain, you can simply just remove the intermediaries where your device directly interacts with the blockchain. So what are the advantages of using DOIT? So first thing could be a direct blockchain interaction via the smart contract. So IoT device integrated with the blockchain can interact directly with the smart contract. So, well, smart contract, as you know, it's a smart contract, which is smart, kind of self-executing predefined rule it has to execute it itself. This direct interaction between the device and the blockchain allows the device to make autonomous decision and take action based on real-time input without the human intervention. This is the first advantage. Second is autonomous transaction signing. Here we talk about the traditional IoT-based system that often rely on external wallets or manual human confirmation to sign a blockchain transaction. This manual signature of the blockchain transaction usually introduce delays or potential inefficiencies. Yes, so it can have inefficiencies, and it can be a problem and long waiting time to process the transactions. So if we have authenticated a device with a private key, it has a capability to do it automatically, the transactions. So for example, you have a private key which is integrated into the blockchain, into the IoT device, and that is processed, that interacts with the blockchain and processes the transactions because it is authenticated to do so. So third could be secure decentralized architecture, which is a tamper-resistant infrastructure. So running IoT devices directly on the blockchain, the system leverages this decentralized nature, reducing the risk of the cyber attacks that typically target centralized system. So each transaction made by an IoT device is cryptographically secured, as you know, and recorded across multiple nodes. So yes, this is one of these are the three advantages which we propose of using DOIT. So a practical use case that we present, where it can be used to have this IoT device fitted to a transport for communicating with the blockchain. So for example, you have a simple transport truck, and then you can simply integrate this device into a truck that will constantly communicate through wireless network with the blockchain and keep updating the information onto it. In future slides, I will tell you more in details like how exactly these things are done and achieved. So a quick overview of what exactly this our IoT device setup looks like. So it consists mainly of three parts. Yes, three parts, which is Arduino, Raspberry Pi, and the sensors. So let's talk about the Arduino and the sensors together. So we use Arduino Uno, which is a central component of the system. It receives the input from the sensors, for example, like temperature, humidity sensor, and so on, and which further processes the data. So this this Arduino Uno can be programmed to take specific actions, like, for example, trigger an alarm, sound a buzzer, and so on, based on the input that it gets from the system, from the environment. So the setup includes three lights, like three LED, which is green, yellow, and red, which are used to indicate the temperature that is detected by the center. So for example, like green light is lit up which is in optimal range. The yellow light is lit up when the temperature is going little beyond towards the danger zone, let's say. And the red is like, okay, it's danger time. Like it has exceeded the range of temperatures that is required for your device. Right. So in this scenario, we are as an input scenario, I mean, for the sensors, we are not using temperature sensor or humidity sensor because it is very difficult to control the temperature of the room. Okay. It is expensive, I would say, to control the temperature of the room or like control the humidity of the room. But for a simple and cheaper solution, we use a 10 kilo ohm potentiometer, which has analog input. That means it has input from 0 to 1023. That is the range of input that you can have. So why do we use this potentiometer? The reason of using potentiometer is because it has manual input simulation. So it enables us to manually simulate the environment conditions. So you can just represent that change in temperature, 0 to high, high to low, and so on, without actually changing without actually creating environmental fluctuation, like, without actually heating or cooling the room, I would say. It is also used for testing and calibration, meaning like if you want to test your system, like only the device, let's not look the blockchain into it. If you want to only test your system, that if red, green light are working correctly, that is where we call testing and calibration also important. Jumping wires, well, jump wires, very important to have all these connections that you have through your LEDs, how it is called, potentiometer and Arduino. Right. So the image on the right that you can see, this is the architecture that we're using to set up your Arduino device. Moving on. So yes, you have your Arduino device, and we have written it, done the programming using the Arduino interactive development environment. They have their own syntax and own programming language. I think it is somewhat similar to C and C#, but I think writing this for writing the programming onto this device, we kept it very simple. So we indicated the input from the sensors, from the potentiometer. We indicated this range 0 to 700 was green, 701 to 900 was yellow, and 901 to 1023 was red. Now this was running in a loop, like kind of an infinite loop. It was running, and it was reading the input from the sensor for every 1 second time interval. For sure, this was just a scenario that we took. You can have variable time sensors and so on, like it's up to you. So yes, so this was the programming condition that we kept. So whenever the range was somewhere between 0 to 700, it was green, yellow, red, and so on, depending on the input that you got. Okay. Second part of the IoT device was the Raspberry Pi. So we specifically interfaced Arduino with the Raspberry Pi 3 Model B. Yes, Raspberry Pi 3 Model B. And this Raspberry Pi has, these are some specifications that it has. So why do we use it? Because it has good 64-bit processor. It is very low costing and efficient to use, and it can do multiple things like a small computer. It can handle data collection, sensor management, communication with IoT setup, and so on. Right. So it utilizes SSH with public key authentication to enable secure remote access and prevent unauthorized entry with private key stored securely on the device. So there is a private key which we store on the device, and this private key is being used to convert to wallet, and then this wallet kind of send transactions during the digital signature and so on. And this action can be done either on through wired cable for sure, but for better use case, it will be Wi-Fi connectivity. Like Wi-Fi is connected with the blockchain, and all the information is being sent and read from it. Okay, moving on. So yes, you have now the full IoT setup device looks like this. Well, not full. The Raspberry Pi of the IoT device was written in Python. So you had to connect the Raspberry Pi with Python and write the programming onto it. So so the script of the Python was divided into 3 parts. So first you had, 2 parts, but second part was divided into 2 subparts. The first one was the USB communication. The Raspberry Pi continuously, the Python script written on the Raspberry Pi is continuously listening to the input that comes from the Arduino device via the USB ports. So this USB ports are continuously listening the IoT device, and after the information that is being loaded onto the Raspberry Pi from the Arduino, 2 things happens. We take a scenario that every 20 seconds, the device checks and records the maximum value that is detected during this 20 seconds period, and prepares to log it on the blockchain. I will come in the later slides why exactly we take an example of taking the maximum value. I'll come to this thing. So yes, and the second part, after taking the maximum value in the 20 seconds time period, the second part that happens is the device, which is authenticated with the private key. It tries the transaction to the blockchain. That ensures only authorized devices can record. So for example, your smart contract has this. So the smart contract, excuse me. Device can record data. So yes, so the smart contract that you have, it has a condition that only the authorized device can write the information onto the blockchain. So we assume that yes, this IoT device has authority to write the information. So now this transaction is automatically signed and submitted based on the rules that is defined in the smart contract. To do this work, we use the Python Web3 library, and this was pretty straightforward to use for us to do. So So why do we consider the highest value in the time frame? It is because of this reason that, for example, that we assume a 10 seconds time frame, and if we take between 50 to 60, if we take between 50 to 60, so what happens here, that till somewhere over here, everything was within the range, but for 1 or 2 seconds it goes the high for in the red zone, but then again suddenly it draws back to the green zone, right? So we do not consider to take average, but rather we consider to take the highest value. It depends on the use case. You can either take highest value, average, or the lowest value. Depends on the conditions, because there can be some situation which should not go very low, should be at high temperature, and so on. This is a scenario. Okay, moving on. So yes, that was the reason we took the highest value in this scene. So if we integrate all the parts of the full scenario, so you have a sensors and LEDs, and you have Arduino that is taking input and giving output, which is interacting with Raspberry Pi, simple, using a USB, and then that is further interacting with the blockchain over here. So yes, in reality, well, in physical reality, this is what it looks like. So here is your Arduino. This is your Raspberry Pi. There are some connecting like this. I think this is giving power, and I think through Wi-Fi, they're connecting to the blockchain. And here is your 3 LED lights, and with jumping wires, your potentiometer that can actually is rotating and checking the value of it. So, smart contract. So yes, smart contract that we deploy for conducting this experiment has these 5 main values. So first of all, there is a threshold zone. So we define a threshold zone, which is yellow and red zone, and also green, for monitoring the product's condition, like temperature, categorizing sensor data, yellow, green, yellow, red, and so on. So based on the threshold value that you get. Then you have the product information. The product information does not define the product itself, but simply tells like who is the sender, who is the recipient, and the transporter, the transporting entity in between that goes. Third is the sensor data logging. So every time interval, like 10 seconds that we, or 20 seconds, well, 20 seconds that we take. So that is this time interval is also being checked from the blockchain, on the blockchain smart contract. So it checks, every time interval, the IoT device records the sensors data, and it logs onto the blockchain with the timestamp and condition signaling, either yellow, green, or red, depends. So we also have a user access control. That means you can either grant or revoke access to a specific address, which ensures only authorized user, that is producer, transporter, whatever, can interact with the product or record the data onto the blockchain, because seller needs to write information and transporter needs to communicate with the blockchain to write the conditions, for example. So yes, and then you have an automated blockchain recording. So this contract automatically logs and product condition, and once you want, it can give you a full kind of a report card, kind of a report of what exactly and conditions of your smart contracts have been working through. Okay, so what a simple use case scenario could be, that you have an administrator, producer, transporter, receiver, and you have a decentralized application. And this is the UML diagram that goes through to that how the workflow of a simple use case is actually being working. Okay, moving on. So on the blockchain, so we deployed the smart contract. Here you can see the contract smart address. Yes, that you can see. And now this is what is something to look into. So here you can see initially the product is dispatched. I hope it's clearly visible for your screen. So product is initially dispatched. So initialized for dispatch. And then the product is dispatched, and the IoT device on the transport vehicle constantly communicating with the blockchain in a fixed time gap. So, well, now it is already 57 days. It has this time frame, but when the experiment was freshly conducted, or if you wish, you can later take the time gap. It is approximately, I would definitely say, that amount of time that took from making in how to say commit was more or less 20 to 25 seconds. So in 1 minute, I think we were definitely having 3 transactions. If 1 minute was 3 transactions, then yes, it was, I think, approximately 20 also, if I remember correctly. Yes. So obviously we did not want it to go long. So we came to a point where the product was marked received. And once the product was received by the intended recipient, you can see the further transaction fails. Fails because because product is received, it cannot communicate with blockchain more. So that is why now you can see it shows like exclamation, it has a failed transaction. Here is a small glitch, not glitch exactly, a small, how to say, problem. Right now, even though if I manually wouldn't stop my device, it will keep on making this failed transactions like this. So after this point, I decided to manually, I had to intervene and stop it, but it was just a prototype and it can be definitely improved upon. Okay, so now let's take a use case scenario for like a real-time use case scenario for transporting a cream cheese. So this product is, the scenario is that we have a product and it requires the refrigeration requirements. So for example, you have a simple cream cheese and it is being transported from New York to California by truck. And the cream cheese requires a constant refrigeration in order to prevent spoilage due to bacteria growth that can happen actually. Okay, so what happens for this transporting? The use case that I said, to transport from New York to California. So there is New York and there is Los Angeles. To have this route, there are multiple stops and drops, and it requires constant refrigerations. And if you have a non-stop driving, it takes approximately 43 hours, approximately 2 days. And since it's a truck and you need to have stop move way, so it will take approximately 6 to 7 days of transportation. Just from the map, you can see this red line that you have. It's just a bird way, and this blue one is the actually route that you have. Okay, moving on. So hypothetical situation was that we have an IoT device setup with real-time temperature monitoring. The truck is equipped with IoT device that constantly monitors and logs the temperature inside the refrigerated compartment, right? And if there is any deviation in the temperature goes outside, like if the temperature goes outside the optimal range, the IoT device trigger a real-time alert to notify the driver. Well, I mean, I don't know how helpful this thing will be, but the driver can be notified that it has gone outside, let's say. So yes, so as of 2023 in US, there are approximately 436 cheese production businesses. And in 2023, there was an increase of 0.9, approximately 1%, we can say. So as you can see, the trend, like there is a small increase in cheese businesses. And when we talk about the cheese businesses, here we are not talking about the big players, but also we are talking about all the small and big, every place. So in sub scenario 1, we registered 117 addresses. Like if you remember, like we grant access to the system, like that having 417 addresses. We took the data of 2021. 417 addresses, like companies are given access. So you can see that yes, it took approximately this much, well, not approximately, it took this much gas used to register companies. And we assume also, second part, that out of these 417 companies, 50% of these businesses would not continue next year. So we randomly take 50% of this. I don't remember exactly how much, 200 probably 8, let's say. We deregister them. That means we revoke the access from the platform of blockchain. I mean, our blockchain platform. And doing this thing, we saw that in order to, well, based on the gas use that you get, you can register at max 641 registration in one blockchain, like in one block of Ethereum. That means we infer this thing like one block of Ethereum can fit approximately 461 registration. So, and to deregister, it is almost double, which is 1208. And I think the reason why it is almost different from registration deregistration, because the registration is kind of giving an access to do further things, to like, I mean, here technically you are setting how to say, flag equal to true, and deregistration flag will be equal to 1. Flag is equal to 0, like it is false. And that is why from the Ethereum yellow paper, that is where the difference comes into, that revoking, that granting access setting true is more than the setting false. Excuse me. Moving on. So now we have second sub scenario. So you have producers that produces products, and we have the package that can be produced by inputting parameters like destination, recipient, transports. The product is created with the package ID1, and it is updated to the blockchain accordingly. Okay, so the transport time from California to New York is approximately 6 days. And this time we are not actually going to wait 6 to 7 days to process the system, but we take the time frame of 24 hours, and also like 24 hours divided by 6 to 7 days. That is not exactly we did. So what we did, like we used a framework of hard hat, and we time lapsed our simulation. And based on this time lapse, you can see the results on the right, that to track the transporting for 6 to 7 days, it is approximately this much gas used, which is also a feasible system. And now, in order to check how much amount of money you will be actually spending, you can just simply multiply the gas used with the price of Ethereum that day. So, but I think we did. I don't remember exactly for this scenario how much what it was, but it was still more or less a feasible system to actually use it. So yes, even though it is not exactly decentralized application that we have been talking into, but still we kind of made a interface like a dashboard where you can actually see some information. So you have an administrative panel there where you can actually get the status of administrator, that does he have access to the system or not. So yes, if he has access to the system, great. If no, you can click revoke access and it will be fine. Third scenario, one more user interface is that you can have the product ID 3, for example. You input product ID and you get kind of a report card. You see, like you get a report card of what at what time, what was the value. Well, ignore the value. It is again the like value from potentiometer that we have used. So the value can go up and down, and then you have a kind of report card in front of you. So you have given this interface to look into it. So the disadvantage of DOT that we have is like, yes, fund monitoring and out of gas failures. So fund monitoring, like since it's an IoT devices, it should always be equipped with funds to constantly communicate with the blockchain. Because if it goes out of gas, like if the funds get finished, your device is also useless, like useless senses unless it get more funds. So there is a way that you keep funding your device, but monitoring so many devices, like we talk about a full architecture of IoT where you have lots of devices having constantly communicating with the blockchain, it can be very difficult if we talk about a lot of devices that you need to monitor. So for this thing, we introduced, well, not our concept, but like we kind of introduced account abstraction to our concept, like this thing. I'll leave more easy to say. So this is the architecture that of account abstraction. So you have a user that creates a user operation. That means which makes the transaction details a signature. You have a bundler which collects all the multiple user operation and send them to an entry point contract. Now, this entry point contract validates and processes these operations. And then you have a paymaster that covers the gas fees, allowing for gasless transactions. And you have smart accounts. I'll come to it a little later. And you have aggregator, which optimizes multi-signature for efficient validation. This information is available more in details on this website link. And I have honestly just a superficial knowledge to use it as an implication in our project. So yes, you have a paymaster, which is a smart contract that pays gas fees on behalf of users, enabling a gasless transactions. Simple as this. So we use Biconomy, SDK, software development kit. We use Biconomy SDK, which is built on top of ERC 4337 to enable account abstraction. So this provides a comprehensive smart account platform, which includes key components like paymaster, bundlers to handle gas fee and handle transaction management as a whole. So specifically talking about Biconomy Paymaster, you have a token paymaster. This model allows user to pay gas fees with ERC token. Please note, not all ERC tokens are acceptable. Like tomorrow, I make my own ERC token and try to launch it on the platform. It can't work because there are some, I think, specifically mentioned ERC tokens that are there. So yes, ERC tokens can be used as a fees, like that can be covered. Then you have a sponsorship-based paymaster that enables a sponsor mode. So where gas fees are entirely covered by a third party, enabling the gasless transaction. So this eliminates the needs for the user to hold native tokens or pay for transaction, thus enhancing the accessibility. So with leveraging these tools, we streamline the user experience and enable more seamless, flexible interaction on the blockchain, particularly for the applications of IoT where the user or devices may not handle token directly. Second. Something wrong with my keyboard. Anyways. Right. So the concept remains the same from the previous part of this seminar, but the overall scenario this time is a little different. So again, we have an admin that is going to deploy the contract. This time, instead of using one simple device like just one device, this time we have 4 devices, 2 of same kind and 2 of different. And we did not have 4 Arduinos, but this is more of a simulated scenario that we used into our system. So yes, we have administrator that certifies 4 devices on the system. So we also scaled, instead of having 0 to 1023, we scaled it like to 0 to 100. That was fine for us. So we have 4 devices. So device 1 and 2 is connected to potentiometer, and device 3 and 4 are connected to ultrasonic sensors actually. And then we created a data set on top of it. So where you have 100 transactions with random values between 0 to 100, and which are 25 for each. So we have total 25 transactions for this, 25 for this, 25 for this, and 25 for this. So we have created 25 transactions. Why did we do this 25 transactions for each device? That means total 100. I'll tell you in future slides what exactly was the concept there. So just to show how things are working, just a workflow more or less is the same, but little detail, like here the device is added by admin. So you can see admin adds the device, then certifies the device, and then you have like send ultrasonic, send potential. So like this is how the system is working. And then what is happening? So at this point, device is uncertified. And then again, this you have exclamation mark that it was not written to the blockchain. And then further, you can remove the device. So this is a simple workflow that this experiment was working. So when we talk about smart account, so in account abstraction, a smart account is a programmable smart contract based account, right? So you have in general in Ethereum, externally owned account, and you have a smart contracts, which are also accounts. And then there is something in between, smart account, which is like programmable smart contract-based accounts, let's say contract-based accounts. So which can have which can do the work on your behalf in simplicity. So how exactly a smart accounts are created? So smart accounts are created by deploying a smart contract onto the blockchain, which acts as an account, right? So when I gave input of this accounts, I'll come exactly what this arrows are. When I launched a smart contract from an account, so smart accounts were created. And in this number of 1, 2, 3, 4, 5, 6, 7, 8, in this 8 list of accounts, these 3 are my accounts, like how to say externally owned accounts. And here are smart accounts. In this thing, one thing you should see, like I have marked arrow red, what I'm indicating is that they have some balance in ethers. Here I want to show they have some balance, and here you can see they have balance 0 right now. It will be clear in the next slide, in for future slide, why exactly we specify that here should be 0 and here should be some balance over there. So yes, yes. So we use this set of accounts to do gas transactions, and you use this set of accounts to have gasless transactions. And we check that the balance have reduced after processing some set of transactions. And here we successfully process transactions without spending any gas. So we had 0 before and after, and here we had some balance, but less after. So in the experimental setup, we have 2 phases. One is gas transaction and gasless transaction. As I said, like this is used for gas transaction, and this set of gasless transactions. So yes, you have 2 phases, gas and gasless. But for saving time and energy, we deployed only one smart contract for both. So here is the address of the smart contract that you have. Now, coming back to this point where we had 25 gas, 25 readings for each device. So this is what it looks. And we process the same readings for gas transaction and gasless transactions. So here you can see one thing very interesting for us also to note, that this is the interface of the smart contract. And till this point, it was gas transaction, which was getting recorded on the blockchain. But if you see later on, we added device, then ignore this one. Then we added device, added device, added device. So here are 4 more. And these 4 device addition, we are talking about these ones. So for sure, you, after generating a smart account from your normal external based account, you need to register it to do further actions. Now, why this thing was interesting from my perspective? Because here you can see that even though we made a gasless transaction, for some interesting reason, probably the documentation will have much better information. For some reason, the transactions that are happening on the smart contracts are technically somewhere not reflected on to the interface. But if we check the matrices, like if we check the smart contract, you will definitely see the information. You like from like last 10 information. I mean, as per the smart contract programming, it exists over there. Yes. So this was quite interesting, probably in further investigation with the account abstraction might be clear, like why exactly this happened. So yes, as you see, this is smart account. So there are no transactions, but here you can see that it has actually interacted with the smart contract of our deployed smart contract, and gasless transactions are actually happening. So yes, in experiment 1, we broadcast this transaction with 5 seconds interval, and we kept minimum balance of 01 test BNB, and we manually added the device and certified it, and then we carried out the transaction in sequence, and we calculated the gas used for each iteration for each device. And there are some more information that we did to make a transaction. But in second phase, We funded the paymaster. We had to fund paymaster with 2 BNB, well, to test BNB, I would say. And that generated smart accounts. We made specifically smart accounts balance to be 0. And then we process the same set of data that we did for the gas transactions into the Gasless, and we calculated the gas use. And in the next slide, we'll show you the difference exactly. So in comparison, you can see, even though the same data was passed to gas and gasless transaction, you can see that gas transactions are comparatively efficient comparing gasless transactions, but it depends on the use case, what you are justifying it for. So I don't think that it is right to say it is almost double, like it is almost double. No, but I think it has a constant difference between gas and gasless transaction. Probably some more work around it, and will be clear to exactly what it is. So yes, gas transactions are definitely more efficient, but gasless transactions are not efficient in terms of gas use, but in terms of processing the data information for IoT devices, still we can consider gasless transaction to be a better choice. So yes, since we have lots of IoT devices, we have a proposed architecture for you. You can have a user that has a master device that has further connected to all the secondary devices that constantly communicates to master device, and this master device kinds of control and manages all the devices in the system. So we used user interface using mobile application. So again, we took an example of transport system. So you have a transport system, well, lots of transporters this time, let's say, which are certified or not certified to do something. You can get all the information, and here you can see a simple scenario of how this uh, information is getting manipulated and changed, which was also passed through it. So in conclusion, our research highlights the successful integration of IoT devices with blockchain technology, which significantly enhances supply chain efficiency and security by enabling IoT devices to autonomously sign transactions direct to the blockchain. We are eliminating the need of external wallets. That means we are ensuring a real-time tamper-proof data logging. Additionally, we are using gasless transaction via Biconomy's paymaster, which is allowing IoT devices to interact with the blockchain seamlessly without the burden of the gas fees. This makes the system scalable also, and also cost efficient, which is crucial for large IoT deployments. Last but not the least, the presented approach also delivers real-time responsiveness, which ensures that the system can handle continuous high volumes of data streams, which make it ideal for use cases like supply chain management, where both the security and speed are paramount. So our work paves the way for more efficient and scalable secure IoT solutions integrated with the blockchain technology. So some future works and direction, which definitely would like to consider, is like a smart contract automation and orchestration, meaning that when an IoT device interact with the blockchain via smart contracts, it enables automated orchestration process. For example, in a IoT scenario, like supply chain and IoT scenario, we can have an automatically triggered clause where certain conditions are met. For example, initializing an automatic payment when shipments have reached its destination, or some type of actions that have been taking place continuously based on the previous input that has been taken. So you take an input right on the blockchain, and the next action in future, in coming time, can automatically check the timestamp, for example, and do some next actions. So kind of an automated, not exactly artificial intelligence included, but kind of an automated autonomous situation to have. Second direction could be image recognition based on digital twinning. So you integrate digital twinning based on immigration and blockchain, where a simple idea could be to differentiate between fake and original product, like differentiator. And second could be a value tagging. Now, what does value tagging mean? Value tagging, so there is an instruction written on the smart contract there is image recognition, which recognizes an object, and it, how to say, give a value, like how much price this value should be, or this device should be, for example, or some item should be, based on the smart contracts conditions and based on the user input feedback and so on. So this is some directions which can be considered. So that was it for my today's presentation. Thank you so much for having me here again. So here are some QR codes which are available, well, which I have presented here. You can feel free to scan and have a joint work, reach out to me if any questions. What else I would like to share? That's it for my today's lectures, well, today's seminar. Thank you.
Thank you, Yash,
Thank you.
so much. Друзья, коллеги, есть ли у вас какие-то вопросы по поводу этой лекции?
Yes, and also, yes, you please ask me any question. Maybe you can ask me in Russian. I will try to my best to understand. And also, I have unmuted people, so you can unmute your mic and also ask questions. I mean, maybe I can, till the time you're thinking, I can also add few words. So this research direction that we are going to work on was also given to some students in the innovation workshop that we have in Schooltech. And Schooltech has an innovation workshop where students need to do some innovative work in 1 month. So one team also took the idea of fake and original product differentiator. So they had done a prototyping, and probably in future with them, and work more in details to it.
So just let me ask one question. Could
Yes,
we
please.
upload your presentation, in our Telegram group? Because I think some people need to know the time, to think about it and, to see some of your ideas.
Yes, please. Yes, please. You have my full consent to upload that presentation on the Telegram or Telegram group, and like whichever platform you want.
Oh, great.
So all the images that are presented, I have provided source. If not, it's my images from my research papers and all, so it's fine.
Okay, so the only comment I see in the chat is, is just Andrei Urusov just, thanks you for interesting presentation.
Oh, thank you for coming. And I'm pretty sure because of a little bit language barrier. So I think more people who will watch the videos later on YouTube will definitely reach out to me with more detailed questions.
Окей, но, друзья, если у вас нету вопросов, то давайте тогда потихоньку заканчивать. Yasha, thank you so much again for participating in our seminar. And, друзья, но на следующей неделе у нас будет новое мероприятие, анонс будет обязательно в группе. Спасибо вам большое.
Thank you so much. Good day. Bye-bye.
Bye.